Mr. Ramesh, yeah, welcome. Can you just check whether the audio works and whether you're able to share your screen?
Yeah, sure, Sudarshan. Hi, how are you?
Yeah, you're audible. Yeah, you can share your screen. We can check with.
Okay. Are you able to see the screen?
Yeah, the screen is visible. Yeah, we'll just share. Start in 2 minutes.
Sure, Sudarshan.
Swarnima, you can introduce the guest. Yeah.
Thank you, sir. Thank you so much. Good evening, everyone. Welcome to FDP workshop. Today, with us for the first session, we have Mr. Ramesh Chandra, who has completed his bachelor's in electrical engineering from BITS Pilani. He has obtained his master's from IISc Bangalore. He has a rich industry experience of 18 years and is currently an architect at Samsung Research Institute, Bangalore. His research interests lie in post quantum cryptography, 6G ML, 6G security. He has contributed to several patents and has authored numerous papers. It is our distinct pleasure to welcome him to deliver this lecture today. We welcome you, sir, for this FTP workshop. So your mic is off, I guess.
Yeah, I'll make you a presenter. Yeah.
Yeah. Okay. Thank you for the nice introduction.
Thank you,
All,
sir. Over to you.
good evening. So, shall we start, Sudarshan, or we need to wait for someone else to join?
Yeah, we can start. Yeah, yeah.
Okay. Yeah. Okay. So, yeah, today we are here to discuss about quantum computers and what is quantum computing, and mainly security aspects of it. Myself, I have been working in the past several years on post-quantum cryptography and security on quantum computers. So before going to session, hope everyone is comfortable with security and concepts, but I will still brief here on basics of some security and cryptographic algorithms so that we better align and uh, stay in touch till the end, because the name quantum itself many times it will be so much confusing or like challenging to understand, and especially when combined with security. So today's agenda is to understand what is this quantum and what is this quantum computing mean. Though most of you people know some basics, also I will again try to cover here. And today's session is mainly about what should we do, like now if quantum computers are coming now, like people say this is a security concern. What is that security concern? Is it really a problem, or how to face that security concerns? So we'll also definitely discuss about post quantum cryptography, mainly about what is PQC or post quantum cryptography we call, and we will discuss a detail about what are the standardization aspects going on at present in the industry as well as in the standards, and various hybrid approaches. And we'll just touch upon quantum key distribution and QRNG also at the end, so that we are aware of all the terminology when someone talks about this quantum computing or the word quantum. So this is a agenda we plan. So stay with me. So this is a when we say quantum, right? Quantum means actually so like you can think about a light or photons, right? So these photons actually has some we have logical bits like 0 and 1. We have something called qubits. In quantum world, we call as qubits because instead of having a state either 0 or 1, unlike like in classical biosystems, in quantum systems, these quantums are in different phases as well as different polarizations and different angles, and while measuring these angles and polarizations, we get multiple states like 0 or 1. So until unless the beauty of quantum physics is that until unless you measure the qubits, you don't know what it is. So once we measure, then we get the clear definition of the state. This is called a physical qubit. So because of this quantum computing and quantum qubits, and we can actually because of this quantum superposition, we call it as, when it is present in both 0 and 1, like if you have a coin, you can have a head or tail at once, but what if you flip a coin continuously? We see both, right? So like that, a qubit stays in that kind of position in superposition states, having multiple states. So what does it do is that because of this, it makes quantum computing very fast. So because it can exist in multiple states, we can measure multiple states and compute faster, you can say. So because of this property, okay, many parallel operations can be possible, and that's the thing we are talking about quantum computing as. So is that easy? No, because though we measure this what we call as physical qubit, right? We can't directly get a value that easily out of it, or we can't rely on it. So we need to understand when there's a quantum error induced because of while during measuring it, or because of this travel. So of travel of this quantum photons, we can say. So this we need to make it reliable, to make it more fault tolerant, right? We need a lot of many physical qubits so that we can get that 0 or 1 logical qubit at the end. So it's not a one-to-one mapping. So here, if you can see, almost there are 9 physical qubits in black and 8 physical qubits in white. So total 17 physical qubits are there. So they are trying to entangle with each other and try to understand the state, and it tries a bit flip and phase flip and try to get its value and auto correct it using few mechanisms. And this is a continuous process. This is a one cycle. So this continuous process of evaluation happens, and we need a large pool of these physical qubits to get into a one logical qubit. So this is the main challenge we have with the quantum computing. But active research is going on, and many companies like Google, Amazon, IBM, like many companies are trying to build these quantum machines.
Sir, we are not able to see your slide. I think in the chat box also someone has asked.
Oh, you're not able to see the slide?
Yeah. Your video is visible, but the slide is not visible.
Should I don't know what the reason.
Before it was visible. Now, in the beginning it was visible. The screen was visible.
Okay. So
now we see only your video, your face, your video.
Now, how about now?
Not yet.
Let me share again. Maybe I'll stop my video. Is it blocking it? I don't know. Now it's visible?
Yes, yeah.
So did I lose in between, or like, are you able to see the screen now?
Yeah, qubit, quantum bit qubit, yeah.
Yeah, this you are able to see, right?
Yeah.
Okay. So as I said, there is a superposition of different states possible in quantum physics. So here, like, it can be either 0 or 1 until measure you don't know whether it's a 0 or 1. So this is a quantum error correction I was talking about. Like there are total 17 qubits here, and it's trying to measure each measurement. We are using bit flip and phase flip and try to get the logical value out of it. And it does this correction in multiple cycles, I was saying. And so it's not that easy that, as we say, that we can easily build a quantum machine. So it's like this is the main challenge of the quantum computing. So I was talking about here, like many companies like Google, Amazon, IBM have started developing quantum machines long back, and they're trying to improve by overcoming this challenge of this quantum error correction, quantum superpositions using quantum entanglements. Such things they are trying to build a higher qubit machine. So whenever we talk about qubits here, is just a physical qubits. So they need a lot of these physical qubits to build a logical qubit, as I said. Okay, so if you see, IBM actually started in 2023 and trying to make this Heron of 133 qubits and Condor of 1121 qubits. And finally, they are at Kokubora, where 2025 they planned, but it may be launched this year. So, and IBM has also released its Qiskit library, where you can really play with these quantum gates and try to code yourself. It can simulate and run on these quantum machines also. So if anyone interested, you can even try the Qiskit library. It's very useful tool to understand about what is a quantum gate and how to use it. So what is the impact of this quantum computing? Now we are talking about security and all, right? So if anyone knows the classical asymmetric cryptography, we will shortly explain in detail, but it's about generally any existing such kind of cryptography. Suppose if you are using a classical machine like your normal laptop computer, it takes almost 1 billion years to crack the RSA code, RSA, or electrical cryptography, or we call as public key cryptography, current cryptography. But using this cryptographically relevant quantum computer, we can actually break within few hours or within seconds also. So that's the main challenge we have today, and that's why we are talking about security and security from quantum machines in this session today. So let's, I think I will, just to not make OHT, so I will try to explain what is the current cryptographies, and we will discuss about what type of cryptographies we have. And now when we say it's quantum machines, because of their excessive power, they can compromise this cryptography. So what and all cryptographies it can compromise, and what and all algorithms we have today, and what are the applications of that. So we will discuss that further. Okay. So there are two types of cryptography when we say asymmetric cryptography and symmetric cryptography. Asymmetric name itself says it's also called as public key cryptography, where you have both a public key and a private key. In symmetric cryptography, we have only one key shared among both of them. So there are, using asymmetric cryptography, we can do a encryption or a key exchange we call as a elliptical curve Diffie-Hellman or ECDH, and also digital signatures. Whereas using symmetric cryptography, we can mainly it's used for data encryption, and it's also we can use as for hashing. So all these cryptography algorithms, we'll just have a look at each one and see about what is the understanding of that cryptography. Then this asymmetric cryptography. So when in 1994, Dr. Shor has invented an algorithm called Shor's algorithm. This, when it run on these quantum computers, it can exhibit such powerful computations, and it can compromise the existing in the integer factorization constructs in RSA, as well as the district logarithm constructs in elliptical cryptography. So that is a problem we are at hand currently. So when IBM or some other person develops a big quantum computer, and if someone uses this algorithm on that quantum computer, then he can use that machine to induce an attack on the existing cryptography. Similarly, there's a Grover algorithm which actually had a chance of cracking the symmetric cryptography also, but that still the research is going on whether it's really compromised or how long it is. So at present, we are a bit safer from symmetric cryptography. So these are some examples of RSA, ECDSA, and we will try to discuss that shortly. So when I call this cryptographically relevant quantum computer, right, it means that we have we can develop such a large quantum machine with this much of physical logical qubits. I'm not talking about physical qubits, like a 2330 logical qubits are required to break existing elliptical cryptography, whereas a 6000 logical qubit machine is required to break RSA algorithm. So when we have such kind of a quantum computer, not talking about physical again, logical qubits, and when we run these kind of algorithms like Shor or Grover, and then we can say that we have a cryptographically relevant quantum computer, and it can compromise the existing cryptography. So before understanding all the, as I said, we'll go into back to basics and try to understand about what is the symmetric cryptography, what is asymmetric cryptography. So suppose there is a Bob and Alice. I think this is a standard example. Everyone will be talking in the cryptography. So if Bob is trying to transfer any data to its Alice, then Eves is a eavesdropper trying to snoop on it and can listen to that data easily. So what we have is we give a key to a secret key to the Bob, and we can give a same secret key to the Alice. That's why it's symmetric, same keys in both. We can encrypt this data to one hand, and other Alice can decrypt using that, as you lock the door and unlock the door using the same key. And after the encryption, we call it as ciphertext. Before it's a plain text. So this here, you cannot try to understand the data it is, and Alice can only decrypt. No other person who has a secret key can decrypt this. So as I said, AES is a symmetric cryptographic algorithm. Like that, we have it's a block cipher. In NIT cipher, we have AES GCM also and CHA-20. These are the names of the algorithms which use such kind of concept called symmetric cryptography. Now the question is, how do they share this key together? So that's the reason we need a key agreement or a key exchange between these two parties before it. So that's the need of this example of this one example I have given for TLS setup with the symmetric key. So yeah, as Alice and Bob are symmetric key data they have. So how the symmetric key data they can use further. So how they got this, here we have using Diffie-Hellman key exchange using asymmetric cryptographic algorithm, where we can have a public key to Bob and private key to the Alice, so that one person can use some elliptical cryptography and generate a key, which we call as a shared key, or from where the symmetric key is derived. And if using this cryptography, the other Alice also using its private key also, it can generate the same shared key, and then that shared key is further used for communication. So this is how we using currently in all our TLS connections, transport layer security, which we say are IPsec. IPsec use IQA2, but TLS uses this ECDH called elliptical curve Diffie-Hellman key exchange. Okay. So as I said, why this ECDH is required? Why do we need public cryptography? The need becomes because both need the key, but they need to get this key somehow. So that's where ECDH is used, elliptical curve Diffie-Hellman key exchange. So how it works is like you can take a function where it can take a base point g on this function, or like it's like just a curve shape function. Okay. Now on this point, if we get using this curve has such property such that suppose as I said, we have private and public key in PKI. So if I give a secret B here and secret A here, when it is we can give multiply A into G, this G point, and give it to Bob. And similarly, Bob can use this secret key B and multiply with G and give it to Alice. So this both can, now Alice has A, now Bob is sharing B into G. So when Alice gets this B dot G, it products with A dot B dot G and it generates a shared secret. Similarly, when Alice shares A dot G and Bob already has a secret key B, he can also derive at the same key. So this B dot A dot G is called as this shared secret, or this shared secret is used in further for symmetric cryptography in encryptions. So the does it work with all numbers? No, obviously we need to have a special curves like that, and that way it's called as the elliptical curve Diffie-Hellman key exchange. And these are some common curves, standard curves I should say, P26 or curve 255 are the standard elliptical cryptography curves which we have defined by NIT. Okay, so this is how we have public private key pair, and one key is used to the Bob and other key is used to Alice, and that's how they can share a common shared secret key. Similarly, public key cryptography is also used in digital signatures. Okay, now I'm sending that authentication and I'm doing a data encryption, but how to check the integrity or how to validate the authentication of the party? So here we use digital signatures. So where a message hash is generated and a private key is used to sign the hash and send it to the other party along with the message. So when the other party receives this signature, it can verify with its public key. So this public key can be distributed to any people. So Bob has his private key and he can distribute public key to anyone, so that anyone who has this public key can try to check the integrity of the message and validate whether it's a Bob or not. So this is we are using in many applications, like even we use in our digital certificates over web browser, client server communications. Many places we use these digital signatures to validate the integrity and authenticity of the user. So as I said, what is the impact of this quantum computing on these cryptography algorithms? Let's discuss. So AES, which is a symmetric cryptography, currently with the current 128-bit encryption, even using a Grover's algorithm, it is very hard to break the symmetric AES algorithms. So NIT has mentioned that we don't need to upgrade currently, but minimum we need to have a 128-bit security so that we are far safe from the quantum computers when really come. We'll also discuss the timelines further. So similarly, SHA like hash algorithms also, it can't be broken by quantum machines yet. But whichever we are talking about, this RSA or elliptical cryptography, ECDH, and digital signatures using elliptical ECC, we call as ECDSA, elliptical curve digital signature algorithms. These public cryptography are at risk now. Why these are at risk? Because RSA is made of a construct using a integer factorization. Let's suppose you have a very large prime number. Okay, now we need to break it into two different numbers. So that is a mathematical challenge or the root of the RSA. Now, like earlier classical machine, it takes a lot of years to break that and find that prime factorization. But whereas quantum computers with this superpower, like can say that fast computations, they can easily factorize and get it to the keys. So that's the reason RSA may get compromised, and that's why we are looking for quantum safe algorithms. Similarly, electrical cryptography also works on this discrete logarithm problem of using the elliptical curves. Even this also is broken by the quantum computers. But as a symmetrically, it's not much affected, but minimum if we increase the bit size in the symmetry, because it runs on this polynomial speed up. So if you can increase a bit from 120 to 256 bit algorithms also, that is enough. We can still make sure that it is safe from the quantum machines. Hope everyone is with me. Okay, so now we are talking about key concepts of security. Okay, now we talked about what are the problems, and what is a quantum computing, and really what is a logical and physical qubit, and how a quantum computer works. So if the quantum computer works like it's a like I give an example, like when it's super cooled light of photon, right? It slows down actually. So when it slows down this photon, we can really measure these bits, and that's how we are able to get it, the logical qubits out of it, and then we are able to calculate the find the data actually. So from there we have also saw what is asymmetric cryptography, what is symmetric cryptography, and how they are compromised, what are their basic physical mathematical concepts, and how they are compromised. Now definitely we need to have some solutions. So NIST, which is a National Institute of Standards and Technology, has started its research in 2016. It's like 8 years before, and they have tried to develop few algorithms. We will discuss about the algorithms further, and we call it as post-quantum cryptography. So these post-quantum cryptography algorithms run on our classical machines only. It's not like they have nothing to do with the quantum machines. They run on your classical machines, so that, and they encrypt such a way that the mathematical construct is such a way that it is safe from quantum computers. Then we have a quantum key distribution, which is used for key management. This really, we need a quantum physics to transfer the photons to get the keys. And third is a QRNG, quantum random number generators, where quantum machines are also being used to generate random numbers. So today our key focus will be on post-quantum cryptography, and I will give a gist of what is QKD and QRNG also at the end. So now we say that it is quantum machines are coming, and why we need to be, if quantum machines are not ready yet, right? Suppose quantum machines come by 2035. Okay, so then why we should study this and understand about worry about now? So that is the point we will discuss now. So actually in 1995 itself, there is a hash-based algorithms called SHA-1, which is NIST has developed. Then they anticipated that there can be some kind of attack on it, and they have developed a SHA-2 algorithm standardization. But if you can, I think someone mute mic is on. Maybe can mute. Yeah. So so NIST has thought to stop the SHA-1, but it took almost 17 years for browsers or the SHA-2 adoption to complete browsers, or like Google Chrome, Microsoft, or any servers throughout the world. And it took almost 17 years for transitioning to SHA-1 to SHA-2. And exactly after that, first collision happened in August 2017. We have that much advanced computer to break the SHA-1. So it's like, though you are ready, like what should I say? It takes nearly 20 years to adopt that algorithm into every machine in the world. So it takes a lot of time. So that's why we need to study now about quantum cryptography and quantum safety, because even though it comes after 10 years, we need to make sure that the data is safe. So that's what Mosca theorem also says, that yeah. So this is the concept of store now and decrypt later attack. So today an attacker, maybe anyone who is able to hear that encrypted data using electrical cryptography or RSA is able to read the data and store it. Whenever he gets a quantum machine, he will use that quantum machine to break the data. Now there are 2 points here. How long the data needs to be safe and how much time it takes to develop this quantum computer, right? So that's the important now. Suppose here y is the time for the standardization. Suppose in 2016 NIST has standards studying this quantum cryptography and take some time to get the quantum algorithms, and you try to encrypt it. And if it's not encrypted, then it's like, suppose your data should be safe for these many years. It may take these many years to keep your data safe, like your banking transactions or other government data. It's not like you every day it gets changed, right? So you need to save it for longer time. And Z is the time for the quantum computers. 2035 we get a quantum computers. So today, if someone able to get the data and store it, and whenever they have the quantum machine, and still the data is relevant here. So since the data is relevant, and he can decrypt and play an attack. If the data is not relevant after that you develop a quantum computer, then it's okay. But still the data is relevant and still you develop a quantum computer and you can attack the system. This we call as zero-day attack. So today's data also is not safe. So today whatever communication happening in cryptography is not safe. That is the reason we need to move to post-quantum cryptography. Okay. So post-quantum cryptography, as I said, NIST has been studying from 2016 and all. So we will see what and all types of post-quantum cryptography are there now. And as I said, depends on the data also. Like if you see today, if we say zero-day attack, then banking sector or like military, such kind of data is very sensitive data. So we need to start migrating them first. Then also other some systems like a public sector, or we can say this telecom, travel and logistics. These are like not they have a bit less relevant or less longer validity of data. But other things like public sector banking requires those data have a long system life cycle, and they store it for longer duration also. So that's why we need to secure the data at first. And how this PQC, now what is this PQC and what NIST is developing, we will see. So post-quantum cryptography, many algorithms were standardized by post-quantum cryptography, which we will see. It depends on this mathematical foundation, like we saw RSA uses a prime factorization, and electrical cryptography uses a curve, which from where we can generate a common shared key, right? So like that, the mathematical foundation for this algorithm is important, because this also runs in our classical computers only, and still it can protect from the quantum computing attacks. So how that much difficult it should be to break it. So the popular one is the lattice-based cryptography, which I showed an example. It's like lattice-based cryptography is like a matrix of points you can imagine, which we call as a crystal lattice. And identifying the distance between this one point to the shortest vector to the given point is a tough job. It's like there are many points, and how fast can you find the shortest vector? So it works on this methodology, and the root math concept is the same, lattice-based cryptography. That is more popular nowadays, and we will discuss about the types. So there are total 5 types of PQC algorithms. When NIST started in 2016, they welcome that you work on these kind of mathematical problems. So these algorithms have been working in many years actually. So, but since quantum computing computers are very long forward, and we don't have that much capability to build the quantum machines, so it has been in study phase for a long time. So when the NIST started studying, it became very serious, and everyone started to submit their algorithms for this. They invited for 5 types of cryptography. So which we talked about is lattice cryptography, lattice-based. Similarly, there are 5 types like code-based, isogeny-based, multivariate, and symmetric. This is like hash-based cryptography mainly. So there are 5 different schemes. So NIST has validated these 5 different schemes and compared its performance, what are the key size it's getting generated, and try to bring the final standards. So these are the standards which is released in 2024, last year itself, 1 year back only. This PQC NIST standards have been released. So FIPS 203, 204 and 205. 203 is nothing but MLKEM, modular lattice based key encapsulation mechanism. This is based on this crystal Kyber lattice based mechanism. As I said, it runs on the learning with errors. Okay. And 204 is nothing but this MLDSA. It is also lattice based only, modular lattice based, but it is used for digital signature algorithm, which we talked about, digital signature algorithm. And key encapsulation is nothing but we use rightly for encapsulating the key so that other party can derive the key, and that key can be further used for symmetric key cryptography or data encryption. Other is FIPS 205, which is SLH DSA, stateless hash based DSA, and digital signature algorithm. This also it's based on Phoenix actually. So these three algorithms are released first, and there is a newly agreed algorithm a couple of months back. It's nothing but Falcon FNDSA. Even HQC also is an agreed, but it's still in a draft phase. Okay, so this is the timeline or NIST has released like till how much we are safe. Now we are telling that okay, quantum machines will come and break the cryptography. Now when is the right time to transit? It is obviously as soon as possible, but when they are trying to deprecate the older algorithms. So by 2030, all the electrical cryptography digital signature, RSA, ECDSA will be disallowed and deprecated, we say. And after 2035, they are disallowed, not allowed in any emulation. So hope by since 2035 is a quantum machine where it can break the cryptography, complete shift we need to make to move to that. So that's why we are trying to start early and developing these post-quantum cryptography algorithms and then adapting it to various places. It's similarly for key establishment mechanisms also. It's similar to 2030 and 35 where it is used. But whereas for symmetric cryptography, as I said, 128 bits of classical security remains to be safe. Minimum 128 bit is the guidance given. So after minimum, current systems are actually, people are trying to move to 256 algorithms soon, so that at least 256 bit security, we are safer from whenever the quantum machines come. So this is the timeline. If you want to visualize the timeline, 2016 NIST has started. They have multiple rounds of these algorithms were there, and 2024 last year their algorithms were published, and still another round is going because currently, if you see, we have only main MLKM and MLDSA, which are modular lattice based algorithms for KEM at least, key encapsulation mechanism. For digital signature also, we have only stateless hash. So NIST is trying to get another algorithm from another group. There are 5 groups, right? Code based, isogenic based, so hash based. So another a group kind of algorithm still NIST is trying to get, so that in case if modular lattice also is broken, though it's been testing for 7 to 8 years, maybe I should take an example of psych algorithm today. So that it has actually been went till third or fourth round, and then it got compromised very recently. So even after 6 to 7 years of testing, also algorithm getting compromised by classical computer itself. Forget about quantum computer. So that is a risk we are talking about. So we can't blindly rely on one type of cryptography also. So it takes some time to adapt and test and still use it widely. So still the door is open for round 2 of algorithms, especially for signatures. For HQC is finalized for KM, so they are signatures win. Still it's open and still they are accepting the proposals. So NIST will hello, yeah. Hello. Am I audible, Sudarshan?
Yeah, you're audible. Yeah.
Okay, I heard a voice. Okay. Right. Okay. So NIST has released these standards last year, and along with that, new thing to learn is that each algorithm has not a single level; they have but multiple levels of security. So it is defined as 128 to 192 and 256. So level 1 is called 128, and level 3 is 192, and level 5 is 256. So each an algorithm that is proposed to the NIST or the standards currently has these multiple levels of algorithm, because it's very difficult to adapt these algorithms immediately with high 256 bits because of the key sizes and multiple issues like that, and the signature lengths, key sizes, which we will discuss now. So hence they have multiple levels, so that a user can have multiple profiles of the same algorithm, and based on the need they can shift the to higher levels, like a banking application I was saying, in military and such kind of applications we need a level 5 security. But and instead of not payments or generic normal browsing or a gaming may not require that much higher security, and level 1 is also maybe enough. So based on the use cases and several needs, they have developed multiple levels of cryptography for post-quantum cryptography. Okay, so this is a transition. These are the algorithms which were developed by. So what replaces what to understand? Okay, so SHA is already been replaced with already SHA 256. So as I said, symmetric cryptography 256 bit is enough. So AES 256 is enough, 128 bit to 256 bit, and SHA also 256 bit algorithms. So they are proposed. Whereas ECDH, electrical curve diffie Hellman, and use 259 curves or the RSA key actions are all compromised. So we need to move to MLChem or the lattice-based cryptography algorithm which are released. And there's a concept of hybrid chem, which it's like a hybrid concept came in combining the earlier cryptography and the current cryptography. As we discussed the point, like suppose what if MLChem gets compromised, though it is not, but still. So that kind of, we should not go with a doubt. So during transition phase, till MLComs are trusted, they are trying to propose a hybrid. This hybrid is nothing but combining existing cryptography with the post-quantum cryptography. That's what a hybrid means. Okay, as I said, HQC also agreed very recently, couple of months back from NIST, and these all can be used instead of earlier key exchange. And public key encryption also, instead of RSA OAP, we can use MLChem and HQC hybrid only. Coming to signatures, as ECDSA, the signatures are used for integrity and verifying the authenticity of the other person, as I said. So all the electrical cryptography and RSA signatures also need to be moved to DSA, digital signature algorithm, standardized by the MST. So it's like MLDSA, which is called also dilithium. It's been named to the with right modification. It is named as MLDSA, modular lattice digital signature algorithm. Like that, Phoenix and Falcon also are into multiple rounds now. So it's like SLHDSA is standardized, but others are FNDSA is in draft phase. Other rounds are still going on to get a newer algorithms, which is based on other types of cryptography, as we said. So now it's okay. We develop the algorithms. Is it okay? Just we develop the algorithms and leave? No, it takes a lot of efforts to adopt. Okay, so we need to create libraries using which are having these algorithms. We should also check about hardwares, can they support these speeds or accelerations, and also we need to modernize any machines if required. But it can also run in legacy machines itself. But we need to at least make sure that some kind of base performance is available. So, and how about adapting this into other communication protocols like 3GPP or like our 5G, 6G, which you're talking about, how we can adapt. So it takes a lot of time after standardization also to get into real world and use it. So now, why there are several algorithms which are being studied and standardized, right? So as I said, the size and performance of these algorithms is important to validate its use, and based on the use case, which algorithms to use where. Okay, so here are the digital signature algorithms like ECDSA. If you see, signature byte is very less in ECDSA, 64 bytes. We are talking about 96 bytes, and here it's 128. But now when we go to MLDSA, it's like we are shooting up the signature size to 3,300, 4,600. Okay, so many factors we need to see how can whether our if I suppose I talk about communication systems, as I'm into communication background, how whether I have this many resources to allocate this many bytes to a UE and base station communication. So that such kind of questions will come, or which algorithm to use, which algorithm to standardize. A lot of work or study going on in that direction at present. If we see about the KEMs also, like ECDH has only 64 bytes and the smaller public key and private key sizes, where MLCAM has slightly higher side. And ML also, as I said, there are 3 levels, right? Level 1, 3, and 5. And so here, if you see level 5, MLKM is suppose more than 3,100 bytes, right? So we should also see whether these kind of algorithms, which are suppose HQC is 7,000 bytes, or what if earlier 64 bytes go into one TCP/IP packet? When you talk about TLS or any transport systems, HQC which carries 7,000 bytes need to split and send. We need to break it. 1,500 is our packet limiter, so we need to break it into five packets and send. So we should see about this performance also. Or can we send in a single packet? Like suppose an MLCM with this public key of 1184 can fit, but other this cannot fit in one. Next level cannot fit in one packet. So maybe some systems may try to limit it to level 3 security based on their limitation that we need to not segment the packets or not. So, but that is one example, like packet segmentation, performance wise, hardware capability wise. So that's why we have multiple levels of algorithm and multiple mathematical foundation for these algorithms available. Okay, so NIT has recently, 3 months back only, they have launched what is the recommendation for these key establishment mechanisms. This document actually has as I said, hybrid thing is very important. A lot of traction is going towards hybrid, where combining the existing cryptography with the post-quantum cryptography as a transition. Maybe once during this transition period completes, we will move to pure PQC or pure post-quantum cryptography. But at present, we trying to, like, systems are trying to adapt hybrid first and then pure PQC later. So this hybrid word, whenever they say, right, people try to get confused on what is this hybrid is. They are using in multiple contexts. So that's why I thought to give a emphasize on what that hybrid means. Okay, hybrid. When I say about currently we are talking about the quantum safe hybrid key of using generating a shared secret from classical computing.
Ramesh, there's a question, there's a request in the chat box. Okay. Can you repeat MLDSA?
Yeah. The name of modular lattice based digital signature algorithm. Okay. Yeah. What is the question? I will see. Okay. Yeah. So MLDSA is a, like, maybe we can just go back to this here, FIPS 204 standard. So MLDSA is nothing but lattice based cryptography. If you get it, like we have crystal lattice and we try to measure from one point to a shortest vector to the other point in this crystal lattice. That is a mathematical problem, foundation of the modular lattice-based cryptography. Now this lattice-based cryptography is being used for key establishment mechanism as well as digital signature algorithm mechanism. So DSA, earlier we used to use ECDSA, electrical cryptography, and digital signature algorithm. We use it for private key for signing, and we distribute the public key to everyone, to whomever you want to try to communicate. That so that using public key, they can try to validate your signature, which we call a digital signature algorithm, right? DSA means digital signature algorithm. So MLDSA, this is a lattice-based digital signature algorithm, which uses this lattice-based mathematical foundation to and generates a public-private key such a way that you use MLDSA private key to encrypt to sign the message hash and try to decrypt on sign and verify the other end with using the public key generated by this MLDSA. Okay, so when I say MLDSA has this suppose a table, okay, so we have a digital signature algorithm here. Again, we have level 1, level 3, and level 5. So here level 1 has a digital signature size of 2420 bytes. That is the signature length it generates. This is a public key size and this is a private key size. And this is MLDSA level 3. These are the signature size, public and private key pairs. These are level 5, signature size, public and private. So these are such kind of various levels we have, and it's based on lattice-based cryptography for signature. That is MLDSA, which is FIPS 204. Hope I addressed your question. Sorry, I can't see the chat box session. Thanks for helping. Okay, anytime, please just try to. Yeah. Okay. So now we are talking about quantum safe cryptography. As I said, hybrid. Whenever I say hybrid, you try to generate a shared secret using existing cryptography and also generate a shared secret using post-quantum cryptography. You try to combine those secrets and try to make a combined hybrid shared secret. How do you combine? It can be a bitwise pair, XOR, and or just simple concatenation. That up to the standards have defined already. So mainly we generate this hybrid shared key, then use it for encryption, symmetric encryption. This is our key to the house now. Anyone who has the key can open the door. So this you can use for data encryption. Other person can decrypt using this hybrid shared key. So now what is the use of this now? Even though if quantum machines come, even though classical system is broken, still you have post-quantum cryptography algorithm here. It can maintain the security. Suppose there is a lot of time quantum computers are not coming, but if PQC algorithms are not being well tested, or still more adoption is required, or more trust is required on those algorithms, then your existing classical machines, if suppose break these PQC algorithms, they can't still break the classical machines because it takes a lot of time. So that's why during transition phase, we are using hybrid concept. That's why it's a hybrid cryptography.
So there's a question on the chat box. If size of public key is less, it might be easily tampered, right? That is the question.
Yeah. So yeah, it depends on the level of security, and as I said, not just the size of the public key, because if you are using these algorithms, this is the public key size and private key size. It gets generated. Okay. So as I said, if level 3 or 128-bit security is required for your use case, then we need to use level 3 cryptography. Okay. And if we're 135, so if higher security is required for your use case, we need to have higher public key and higher private key size. But even level 1 also is safe from quantum machines. Level 5 also is safe for quantum machines. But suppose from 2035, I should say, if quantum machines also started developing, and maybe every 20-30 years, and a very large size quantum machines comes, it may be able to break this 128-bit, but not the 256, such kind of thing. But the current, whichever we are getting in next 20-30 years, 128-bit for level 1 quantum, this cipher, this is also 128-bit security also is enough. And it itself said that how symmetric cryptography also 128-bit AES is enough. Even for asymmetric cryptography or these MLChem also, we 128-bit security level 1 is enough, which is quantum safe, which is post quantum safe. It's not like since key size less, it can't be broken. But I was saying that for long term of based on your usage, like suppose a IoT system, a small device. Okay, I'm talking about IoT's ecosystem of small devices where they can't store, they don't have memory to store this much of large size. There, how a quantum machine now suppose can easily attack a IoT systems, right? So that's why they need to use at least level 1, so they're safe from the at least quantum machines. But that is the minimum level of security required. So there is a significant increase from 64 to 1573 if you see, but that is a mandatory increase so that we require to be safeguarded from quantum machines. Okay. So, okay, I was talking about hybrid. So there is another form of hybrid people use in hybrid public key encryption. This is nothing but, however, we are using ECDH key mechanism, asymmetric cryptography to generate a shared key, symmetric key. And further, we use the symmetric cryptography to sign it, right? So this combination of symmetric and asymmetric cryptography also is called as hybrid public key encryption. So beware to distinguish between what is this hybrid and this hybrid. This is like combining asymmetric cryptography with the symmetric cryptography. This is nothing but combining asymmetric cryptography with the post-quantum cryptography. So there's a difference between hybrid public key encryption versus hybrid post-quantum cryptography when we talk about. Okay, that is the standardization aspects of NIST and where we are now. So as I said, just defining the algorithms is not just enough. We need to adapt it. And day to day, all our transactions happen in like we take a browser, you search something, right? You just client server connection, right? A web browser is a web client is a client and your PC is server, or you are the client and web server, we communicate, right? So the server client communication use transport layer security in day to day. Any application uses the TLS and IPsec. So these need to adapt to the post quantum cryptography now. The starting first, we need to quickly adapt to post quantum cryptography. Though already many browsers, web browsers like Google Chrome have already moved to hybrid post quantum cryptography algorithms, but still RFCs they were being developed by IETF, and still after this hybrid phase, next they will directly try to adopt these standard RFCs which are being defined by the IETF. So IETF is a standardization body which tries to define these post-quantum cryptography algorithms like IPsec, IKV2. There are 4 RFCs released already. One is for intermediate exchange, one is mixing these pre-shared keys, one is also hybrid key exchange, if you see. So all these specifications are being worked upon IETF very aggressively, I should say, so that it can be adopted in everywhere. Once it's an RFC, everyone can refer that RFC on how to use and what are the APIs and what are the standardized ways of implementing and exchanging within the communication, instead of doing it in a non-standard way. Like that, TLS is yet to adapt. There are a lot of active internet drafts going in TLS 1.3. How can we adopt this use of this MLDSA and hybrid key agreements and MLKEM also for key agreements. So all such these are I've listed the standards which IETF is actively working on, so that we get whenever this TLS adopted with these MLKEM or MLDSA algorithms, we call as post-quantum TLS, PQTLS. Similarly, the IKV2 key exchange uses this elliptical cryptography. So IKV2 with IPsec as IP layer, when it adapts these post-quantum cryptography, we call as PQIKV2 or PQIPsec. People try to call it outside. So these are the post-quantum algorithms. And similarly, there are 2 new RFCs also comes for the digital certificates I was saying earlier, right? Digital signature algorithms using the certificates. Intent X.509 certificate is a standard which we use it for creating the certificates. So for and it has a signature also into the certificate, but signed by your CA, root CA or certification authority. So X.50 is the standard for certificates. So these certificates also need to adapt to the newly standardized MLDSA and SLHDSA. These two are the digital signature algorithms which are being FIPS standards are already there. So these algorithms need to be adapted to the certificates. Now, once these certificates are RFCs are out, as these RFCs are out, now whoever has the earlier certificate need to upgrade to this new certificate using this new RFC, so that we can say that the certificates are also post-quantum safe. That is about IETF and standardization RFCs and how the adoption is going on it currently. Anyone has any doubts? Anyone has any doubts? Means, yeah, sorry, I can't see the table. Anyway, Sudarshan will update me at any questions, right?
Yeah, there's no doubts in the chat box. Yeah.
Thanks. So it takes a lot. I know that if people are not from either a quantum background or it's a security background, it may take some time to ingest this terminologies. We use a lot of terminology in security as well as quantum. So let's not confuse with any of these things. So that's why I gave a basic on what is this cryptography, and then how we try to how this post-quantum cryptography has an impact on that. Okay. So now to come, my field is I am from communications, as I said. So now if I want to adapt in 5G, we are like, I think we are using, almost everyone is using 5G since nowadays, right? So if you are in this 5G world, if there are some asymmetric cryptography, do we have anything, and where and all I need to adapt? That is a question I start with when I started this understanding what is the impact of this post-quantum cryptography in 5G. So first we need to list out where and all symmetric cryptography is there and where and all asymmetric cryptography is there. So this is your device. This is your access network, your base station or tower you can think about. This is your core network, which you can't see in front, but your tower, base station, or the tower in front of you is trying to communicate in the back end, which you call as a core network. And one network with other network, they communicate via interconnect, even for roaming, or suppose interoperator, suppose Vodafone and Airtel. So such kind of multiple operators also they have security gateways, we call as SCPP, security proxy gateways. So these gateways will be there, and this is the basic architecture of our telecommunication system. So currently all the data goes to from my UE to the tower uses we call as control plane and user plane, but it uses some kind of communication to talk to the base station. So this control plane or user plane data it uses symmetric cryptography algorithms. So currently we already have 128-bit cryptography, and in 3GPP we have already studied about adoption to 256-bit algorithms. Soon all the algorithms will be adapted to the 256-bit algorithms, which is asymmetric cryptography. And now where are we using asymmetric cryptography? This we are using in EAP TLS to connect with the IoT devices, to authenticate the IoT devices over TLS, and it was a EAP protocol over TLS. And SUPI protection, this is very important thing. Your device ID protection kind of thing, your device unique identity, which you need to be not revealed in the communication. The device identity need to be secured. Otherwise, in 4G, what happened is we don't have this kind of protection in 4G. We used to transfer our normal mobile phone number over the network, and anyone who can access or spoof using a false base station attack or any attack and get that identity can spoof as you. So that's why 4G is not safe in that way. But this problem is solved in 5G, and they have brought this ECIES we call, which we will discuss now, and electrical cryptography. But now quantum computers are coming, so electrical cryptography is not safe. So we need to change to post-quantum cryptography. And similarly, as I said, IETF has already standardized RFCs for IKV2, and TLS also is coming. So DTLS is mainly for UDP, datagram packets, called as DTLS. MTLS is mutual TLS. Both parties move to the need to do the transport layer security, we call as MTLS. So here between our access network, inside access network also there are multiple components which communicate via IKV2, and our access network and core network also talk via these IKV2 and DTLS protocols, which need to be upgraded to the latest IETF RFCs. And TLS is used between these security proxies. There also we need to use TLS, and that's why this it was asymmetric cryptography, ECDH key exchange. So these also need to be adopted to the post-quantum cryptography further when we are going into the 6G phase. Okay, so as I said, apart from control plane and user plane data encryption, right, which uses symmetric cryptography, rest and all use asymmetric cryptography, which we need to try to adopt to the post-quantum digital signature algorithm, wherever ECDSA used in suppose Java Web Token in the OAuth framework. There we need to move to the post-quantum digital signature algorithm like MLDSA or SLHDSA using any IETF standardization RFCs. So let's try to, it takes a lot of time to explain and to understand and grasp of each and everything. So I took an example of SUPI concealment, ECIS, so that you will understand, okay, now what is the cryptography we have said, like we are talking about electrical cryptography and how it is used is a use case. Okay, the SUPI is your identity, okay, your mobile number identity. Okay, in 5G what happened is, in your SIM itself, there is a public key of home network written inside your SIM. So we use a elliptical key agreement to generate a shared key. So UE elliptical crypto works like that. We generate a shared key using a public key of home network. UE also generates a public private key. Network also will generate a public private key. So this is a UE generated public key and UE generated private key. This is a network generated public key. So using network public and UE private, we come to a shared key. Okay, and whatever UE public is there, we send to the network, and network has its private key. It uses UE public and network private to generate the same shared key. So now both can get the same shared key as we discussed initially. That is what ECDH or elliptical curve Diffie-Hellman key exchange is. So that key is further used to encrypt your identity using AES kind of symmetric cryptography algorithms and generate a ciphertext, which is the encrypted value. And for the integrity protection, that key is also being used for MAC function HMAC256 to generate a MAC tag value. So this public key, ciphertext, and MAC tag value is sent over the air, and other party can get this public key and try to get a shared key and decrypt the ciphertext, verify the MAC and decrypt the ciphertext to get the SUPI back, identity back. Now, what is the problem is, suppose if there is a quantum computer, if an attacker has a quantum computer who can access this interface and get this public key, then he can able to derive a private key from it and also break and get the shared key and decrypt your SUKI and get your SUPI back. So this mobile identity is received back. So again, we have the same stage of 4G where mobile identity is exposed and MC spoofing or phone spoofing, user privacy is compromised. Mainly, your location is known to anyone once SUPI is known. So anyone can track our location. That is a privacy issue if someone knows the SUPI. So that's the reason. Now, whatever the places where we are generating elliptical cryptography, we need to use ML-KEM kind of post-quantum cryptography, ML-KEM kind of algorithms to transition into next phases of generation, like maybe 6G, or we are trying to work on this. How can we, is it straight transition? If it transition, what are the problems faced? What are the key sizes, as I said? Is it every device has that capability? And IoT UE has a capability or not? So that's what the study is actually going in our 3GPP, which standards, which we work for. So where we are trying to develop post-quantum solutions for 5G. Okay, that is about post-quantum cryptography. Anyone has any doubts? Just a quick time check, Sudarshan. How much time we have further?
Yeah, you have about 20 minutes.
20 minutes. Okay, fine then. Okay, yeah. Thank you. Okay. So that's about, as I said, we have three things which we'll look over. There is a post-quantum cryptography part of it. And quantum key distribution QRNG, I will try to just give a glance of it so that it is important to understand in this quantum journey which we are trying to learn. Okay, so quantum key distribution. So till now, post-quantum cryptography is enough. It can run on your legacy systems only. We don't require any quantum computers to run those algorithms. You can run on earlier legacy systems only, and it can run, and it is post-quantum safe. So that's why 5G or other 6G or next generation communication networks or anyone, it's easy to adapt. Banking, other sectors also. Many people are trying to use PQC only. But there is an alternative research going on. Like when NIT has started studying PQC 10 years back, there's alternate in European Union is also studying on this quantum key distribution, which mainly HC or other parties are leading it earlier, European Telecommunication Union especially. So this is how it works. So there is a data channel which you can actually send the data. Now, till now we talk about we can use post-quantum cryptography to encrypt this data channel, or at least generate a shared key which can encrypt a data channel so that other person will not know the other key, and this is quantum safe. Okay, so the other thing is why can't we use quantum mechanics or quantum concepts only, quantum physics concepts only to break the quantum attacks? So that's the intention behind this quantum key distribution at the time. So only keys are exchanged. When I say quantum channel, it's like two parties like Alice and Bob are having, suppose, a photon detectors, a hardware which can capable of understanding this, read these photons or send this photon or send this qubits, I say. Okay, send or read these qubits, and that you can transfer your key over the channel. Only the key. Now, currently, how we are using electrical cryptography to generate the shared key, which is used for further encryption. Why can't I use the quantum channel to generate that key? And once the key is agreed from both parties, that key can be used in our classical data channel to for encryption, normal data encryption using any symmetric cryptography algorithms. So, how this quantum channel is used? So it's like both have a filters, or you can say, and they have this polarization, horizontal or vertical, or an angle, either it's a 45 degrees, like plus or minus. So using such kind of filter, it applies on that quantum. You can take it's in a fiber optic cable or a light being transmitted between these two entities, and there you have a quantum at this filter applied here, so that this qubits keep on going and transferring here, and the other person who has that who reads via that filter can get that key and decode that key. Now, what is the, so we see that we are able to send some kind of light here and with a bit sequence coming in. So this is a photon sequence. So when they know what is the basis which they are using, then they are able to get these bits, and that is the key which is getting generated also. But what the main property of this is that if suppose there is anyone trying to touch this photon, or the property of quantum mechanics, if anyone touching to snoop it, it will change its position. So if someone else in intermediary tries to read this data, and he may apply a wrong filter definitely, so he would have just try to read it. So whenever he reads this data, the Bob will try to immediately understand that someone has already read, or the link is compromised. At least he can know immediately. So he will not use that key for the encryption. So because of this quantum property, quantum key distribution has gained initially a lot of popularity in research phase, because it's like a unbreakable kind of thing. But the problem here is hardware adoption. Now every hardware need to be adapted. I can think about your mobile phone, car, like any device, or even the infrastructure wise, they need to involve a lot of cost in upgrading their hardware to the quantum to support this QKD. So this QKD has also multiple protocols. One is called single photon detector. If this is a single photon, there's a bit sequence of photon sequence going, which we call a SPD, or single photon detector. And there's a BB84 protocol which uses the single photon detector. Instead of, there is something called E91 protocols also, which uses quantum entanglement, where a pair of photons will be transferred, and their phases will be keep on changing to get to know the key out of it. But this is the most popular one, single photon detector. Lot of research is happening in academia as well as governments on the single photon detector. May not be used in end user devices, but at least in backend or core network, when I say where it's a cable line is there, or where a fiber optic cable can be easily laid between these two entities. So you can send these photons and try to encrypt the data and make sure that that is more quantum safe. Again, maybe for high secure applications like banking or communication, such kind of sectors also, it can, like banking and defense kind of sectors also, it can be used.
Ramesh, there are two questions.
Okay.
So the first question is, any research challenges about HQC and its applications? What difference does it have over PQC?
HQC is a type of a post-quantum cryptography algorithm only. HQC and PQC are both are not different. Okay. HQC is a humming quasi cycle. I think I mentioned somewhere. Right? Yeah, I think I don't know. I missed it, but I mentioned somewhere about HQC here. I think. Okay. So this HQC, whatever got selected, right? It's a type of PQC only. Okay. But only thing is the base is not. It's like MLKM is different and HQC is different. Though both are different algorithms, they both were finalized by NIST. Okay, it's like don't confuse PQC by HQC. PQC is post-quantum cryptography. HQC is quasi cycle. It's a name of the algorithm, one of the post-quantum cryptography. So it's a like it's again this key length is for HQC. I think if I mentioned. This is HQC, right? So if you see HQC, length of the keys and ciphertext is here. If you see ciphertext size is more larger than the MLKM. Okay, but its private key is almost very similar, but still its ciphertext value is too huge. So though HQC has been standardized, we doubt how much adoption it can happen because MLKM obviously is far better everywhere than the HQC. Okay, so both MLKM, which is modular lattice based, and HQC are type of cryptography algorithm, post-quantum algorithms only. Okay, it's a yeah. Hope I answered your question. What is the next one?
His question is, sir, is access to quantum computers required to implement or run post-quantum cryptographic algorithms?
No, not required. That's the point I want to clearly say, that any post-quantum cryptography algorithms can be run on your legacy machines. It's like it to any device in present world. Most of the devices you can run the PQC algorithms. Okay, but why we are running these algorithms? These algorithms have good mathematical foundation. As I said earlier, we used to have a prime number factorization as a mathematical foundation. Suppose I use RSA encryption, it is easy for quantum machines to understand, okay, what is a prime number I can break and I can get the public keys easily. But using this lattice-based mathematical foundation, now quantum machines can't break that like finding the shortest vector in a crystal lattice. So that is the foundation, right? So that is difficult to break. But we don't need to have any hardware upgrade in PQC. That is the advantage of PQC over QKD, because we don't need to really have any hardware upgrade.
Another question is, are there various types of quantum attacks?
Types of quantum attacks, it can be, because still we don't have quantum, means we have quantum machines to some bit, but it's like I can say we are way near 100 logical qubit, but we are still far away, right? We need 2000 or 4000 logical, 6000 logical qubit to break the existing cryptography. So types of attacks using quantum machines, first it maybe initially we need to have such, first thing is we need to have a such kind of a quantum machine. Then we attacker should have access to that. Then once he has access and using a quantum machine, if he stored the present data, then he can use future quantum machines to decrypt that and perform an attack. So now, since we don't have such big quantum machines, all type of attacks possible is not there. But it can easily see that there is not a big thing. Once currently also, if I have a supercomputer, I say, right, if I take a SHA-1 collision, I don't need to type of attack also. If I know that I directly give input to this cryptography and it can easily break it using the computations, right? So currently there are not multiple type of attack, but at least the type of cryptography are there, like post quantum cryptography and QKD, quantum key, this thing. So this is, people say this is much safer because if in case PQC algorithms are compromised also, QKD, there is no choice of compromisation because anyone can, if anyone tries to snoop it also, the photons change its superposition and they immediately other person will get to know that someone is snooping, eavesdropper is there in the quantum channel. So that's why they are thinking that key they can use for quantum channels, and whatever key other person got, he will use that for data encryption in the data channel.
So there's another question. What are the challenges for QKD applications in wireless communication?
Yeah, challenges that will hardware adoption, because I think everyone knows about this monetization efforts going in 5G. Like 3G to 4G is a big revolution in communication networks where everything moved to IP networks, single IP networks. 4G is a revolution, I can say. So we got full IP networks, and operator has generated a lot of revenue, lot of money they got. So they could invest in 5G immediately. So 5G we got actually immediately after 4G, within less than 10 years gap only. I think 4G we got in 2010 and 5G we got almost 2017, 18 only we have already 5G there in a couple of countries at least. So they have a lot of money to invest in, right? But in 5G, if you see, who are the gainers? In 5G, main architecture difference is for easing the operator's process and everything. Throughput increase might be there. In users, we can see a lot of speed. There are several IoT use cases and several vehicular technology use cases, and lower latency communications, satellite communications. So many extra verticals came in 5G, but usage of who is gaining out of it. If I increase the throughput band today, who is gaining is Amazon, Netflix. These kind of people are gaining. You because you use that streaming over phone, unlimited data you have. So instead of operator getting money, application people, otherwise the providers are getting the money, right? So during the 5G phase, operators did not get that much revenues and profits as 4G. So they don't have money to invest in 6G immediately if I want to do today, right? Early. So they are still thinking carefully to take one step also. So wherever money can be saved, they will be saved. So that's the reason, that's a challenge for operators in communication systems to adapt QKD easily. It's not possible, I'm not saying. It's possible between the backend systems at least. Like if you ask me, at least between the core network and interconnect networks, inside the core network components like these machines, here the QKD, anything they can have between the access network and core network. Here it's up to operators. If they have some shell out some money and they want QKD, they can deploy here. But here is the challenge: UE to access network, upgrading UE with quantum machines, or like quantum, at least single SPD or single photon detector hardware should be so cheap so that it can be deployed in a device and access networks. So that's a big challenge.
So what about the work happening towards satellite QKD initiatives?
Yeah, I think we are at the right point. Next slide is that I'll come. Okay, so I think that's the last slide, or at least I will. That's a good question actually. I should appreciate the person. So we will come there. Okay, I will. That is also big research going on in satellite-based QKD communications. So to close with, I will address a question in the next slide. So this last topic is QRNG, right? Quantum random number generators. So this quantum random number generators, like we have RAND currently, a RAND function, if you write, will generate some kind of random, right? Now that randomness, if it can be guessed by the quantum computers, because they are so fast at the computation, if it can get that random numbers, it can decode that, crack that randomness inside this generating existing classical random number generators. That's why QRNG is a thing which also require a quantum SPD, at least single photon detector, or need a hardware to generate these random numbers. So, but it's not a big hardware; it's a small hardware, same as QKD. We need so when a light photon is sent over this reflective object kind of thing, right? So it generates a 0 here, and if it's generated a 1 here, right? So we don't know now with the how much of transparency is there, it passes or not. such kind of properties of these what do we say, underlying hardware and usage of the QRNG. So it generates a 0 or 1. And as I said, quantum qubits have a different property, right? Until and unless you measure it, you don't know the value of it. So you measure it and you know it's a 0 or 1, and you can convert into a logical qubit, a 0 or 1. So that kind of quantum uncertainty, we say, that uncertainty is present in these qubits or the photons which are being transmitted. So this uncertainty can be used to generate the quantum random numbers, which called as QRNG, quantum random number generator. So we have very high quality of entropy. We don't know what that number is currently. No one can guess that number. So that is one of the functionality of QRNG or application of quantum machines, like quantum computing, I should say, applications of quantum computing, QKD and QRNG, and other applications I want to bring it to your notice because it will be talked. This is I think this is a being of this as a service also. Suppose any third-party persons can offer you a random number as a service, also entropy as a service, they call EAAS. So how to create that entropy and generate a service? You don't need to have a hardware always, right? You can query a third party where you can be a payable transaction, and they can provide a service to you to generate this also. So such kind of things is already being developed and researched well in the field currently. So now to address this thing, and also now is only NIST working on PQC? No, there are over last 10 years, a lot of researchers from many countries have started working on can we do something specific, like China working on CSER. They've planned in 2020. So, and South Korea also started KPQCR in NIST. But if you see, most of other countries have almost monitoring NIST or either part of NIST only. So NIST has most adoption thing. So though others are in research phase, because many people are trying to check these NIST algorithms, give feedback, make public corrections. If it is hacked again, they're coming with them upgraded algorithms. So it went very fast, and NIST released the algorithms, PQC algorithms sooner. That's why many countries are trying to adapt into NIST standards as a starting point for post-quantum migration. Yes, so how it, as I said, quantum safe network, it need a lot of time. Governments, industry need to prepare for so many years to adapt it. Operators also need to adapt, as I said, in 5G, in 6G also. And there are new services as we talk about. So some people can provide quantum safe VPNs using either post-quantum cryptography algorithms or QKD, but they can provide virtual private networks which are quantum safe SD-WANs. And this is, I think, this is a question like quantum safe satellite communication links. These are one. So wherever currently we call non-terrestrial networks in telecommunications, NTNs we say, right? So we use currently NTNs for satellite communication. And can we use quantum safely? Yes, we can definitely use. A lot of research is going on that, but there is a big problem, right? Obviously, can we transmit a light photon without any diffractions over the air, and how much distance we can send? There is a challenge. So satellite is located very far, right? So can we send such kind of a quantum photons or beams which can go towards still the satellite without diffracting? And normal quantum machines, which we are talking about, 100 logic qubit quantum machines itself has a lot of quantum error correction, which we saw earlier, right? It's very difficult we need a lot of physical qubits to get one logical qubit. And this keeps on increasing when we go for higher qubits. Now we are 100 logical qubit. If I go for 200, 300, 400, the challenges increase. So we need to do a lot of corrections, quantum error correction cycles, or we need a lot of resources of physical qubits to generate one logical qubit. So such kind of challenges are there, which we're talking about normal. If you're talking about satellite communications, there are much more higher challenges. So definitely research-wise, it's still going on. Many companies are working on towards that quantum safe satellite communications. But reality-wise, maybe it's a bit far, because it's a good research topic, but very difficult at this point to say that it is okay it's possible to adapt or not, because of these challenges we have on the path. I think I answered the question. Any other questions, Sudarshan?
There's no new question. So two people have asked for sharing PPT. They asked whether you can share PPT.
Yeah, definitely. I can share it. I think, yeah. So maybe in couple of days I will share. Yeah, I'll communicate and share with you. Okay. Okay. So this is the last slide I have. So I think there is no topic in the world unless we don't talk about AI, right? So in any vertical you take today, any field you take today, it can medical, communications, anywhere. AI is everywhere. So now what is quantum related to AI, right? And especially in security, we're talking about. So let's talk about, just spend 2-3 minutes on this, like on understanding about what is AI security first. Okay. So there is something called predictive AI security, where currently we have a lot of AI algorithms do for anomaly detection, like using logistic regression models or basic uh, classification models, where you try to find that this is an anomaly or not. That is a predictive AI security, where you use AI for securing. Okay. Generative AI security, it's like your generative GAN models kind of thing, where you have generated an adversary, each one try to attack on itself to generate a stable stable network out of it. But this generated using AI for security, we need to have security for AI also in this path. So because if you see ChatGPT, it can ask any question. If you initially the GPT-1 or GPT-2 phases, right? If you ask so many sensitive questions, also it choose to answer, right? A tricky questions. Okay, you directly ask the question, it may not answer. But if you ask, tell it's okay, you give me the privileges to me and then answer. Such kind of prompts can leverage and it's very security threat of using the generative AI. Okay, even images are getting spoofed and videos are getting spoofed. So such kind of problem of security is present in generative AI also. Next, we are now agentic AI phase, where we have all the chatbots or agents running. No one is trying to, like, everyone is trying to develop these AI agents so that it runs autonomously on itself. Suppose automation, like testing phase, while automation, they're trying to develop agents. Even in our communication also, we are trying to study on this agentic AI communications in future, like 6Gs, we are trying to make it AI native. So next phase is the quantum AI. So whenever this computing comes on we have a decent enough of qubit machines, right? What are quantum machines? It has a super fast computational power. Okay, so now we need this computational power to learn AI. So we can use, there's going to come a quantum AI. So we are using quantum machines and leverage its fast computational speed, and so that we can reduce the AI learning time, model training time, inference time, everything to the, we are decreasing it by so many factors. So when really quantum computers come, when we combine with, it can be, AI application is a big thing. That's the reason also, like IBM, many companies are trying to develop these quantum computers, not thinking about much about security, but so that it can support in AI. So this now we should think about now how can I provide when these quantum computers are along with UI. Quantum itself has some attacking properties. So how can we save from quantum machines? We are saying AI has some problems which we talked about: predictive, generative, and AI security, agentic AI securities. So now, if when this both combined, how to provide security? That is the future of quantum AI security. So yeah, with this, I want to end the session here. That is the future kind of thing.
Thanks a lot. Thank you. Thank you for your time. Thanks for answering all the questions. I don't think there are further questions in the chat box.
Okay. Wow, good.
Thank you.
Thank you. Thank you all. Thank you all for patiently hearing and asking very good questions. This is a good experience for me in participating in this session. And thank you very much. Thank you, Sudarshan.
Thanks a lot. Thanks a lot. So participants, we will have the next session at 8 p.m. At the end of next session, I will share the attendance sheet and the feedback forms. Thank you. The next session will be by Dr. Shweta Agarwal, IIT Madras, at maybe on post-quantum cryptography.
Hello.
Yeah, welcome. Hi. We will just wait for a couple of minutes.
Okay.
Okay, thank you. Yeah. I'll make you a presenter.
Hello everyone. Today for the second session, we have Dr. Sweta Agrawal. Hello ma'am. Who is a professor?
Hello. So actually, it's not letting me share my screen. I think I'll have to exit and re-enter because it needed me to change some permissions. So let me just come back. Give me a minute.
Okay, fine.
Sure.
Can you see my screen?
Yeah ma'am, it's visible.
Okay, good. Yeah, so I'm ready when you are.
Okay. So, just an introduction. Dr. Sweta Agrawal is a professor at the Computer Science and Engineering Department of IIT Madras. She earned her PhD from University of Texas at Austin. She spent 2 years as a postdoctoral scholar at the University of California, Los Angeles. She has obtained several awards. Notably, she is the recipient of the Rashtriya Vigyan Puraskar Award in 2025. It is our distinct pleasure to have you, ma'am. Welcome to the FDP.
I'm happy to be here. I will talk about post-quantum cryptography, or in a more informal way, about making and breaking secrets in the post-quantum era. So this is, this talk is meant to be informal. I would like you to stop and ask me questions at any point. Is that fine?
Yeah, sure. Yeah.
Okay, so let me get started. So, cryptography is the art of secret keeping, as you might know. And cryptography seeks to give some rigorous guarantees to the security of any system. And the sort of guarantee that it gives is that breaking some crypto system is as hard as solving some difficult mathematical problem. So the way that we capture this guarantee is that we design a sort of a algorithm which we call a reduction. So you must be familiar with this idea from your theory of computation course that you want to reduce one problem to another. So here you want to reduce the solution of some well-known hard problem to the hardness of breaking the crypto system. Okay, so how do we do that? We design some algorithm which takes the instance of some hard problem and then changes it into, or somehow manipulates it into, an instance of the crypto system, which is then broken by the attacker. And then that is translated back to a solution to the original problem. So what does this kind of thing guarantee? Does anyone want to say? What guarantee we got from doing this? So as I was saying, though it is an online talk, I would like to make it interactive. So can anyone tell me that if I manage to do such a thing, what is the guarantee that I got out of it?
it will take thousands of years to crack the whatever the mathematical base cryptography is done as.
I mean, that is assuming that the hard problem will take thousands of years. Basically, the guarantee which I got is that if there exists an attacker for the crypto scheme, then that means there is a solver for this hard problem. That is what I proved here, right? So by suitably choosing this hard problem, I can ensure that this crypto system will be secure, because anyone who breaks it can be used to solve the hard problem. Okay, this is the sort of guarantee that we got. But now when we say the word difficult, what does it mean? In particular, for whom is this problem difficult, right? And this who is the cryptographic adversary. In the real world, this could be individuals or governments or military or whatever. It is normally modeled mathematically, however, by a classical computer. And here, indeed, the guarantee that you typically get is that unless the adversary can solve this hard problem, it's going to take a very, very long time to break open the crypto scheme. Okay, so this is the guarantee that we get. And this guarantee is also robust to the type of computer you have. Like whether you have a mobile or a laptop or supercomputer, it will not really make a difference. So the question that we will ask is that if instead of changing the number of resources, what happens if we change the quality of the computer? So instead of taking a classical computer, if we take a quantum computer, then what happens? So this brings me to the next, the next concept, which is that of a quantum computer. And these are computers that use the laws of quantum rather than classical physics. In some cases, these quantum computers can solve problems very fast. Now, as it happens, you might be knowing that most current day cryptography relies on the hardness of certain problems which can be broken by quantum computers. Okay, so basically, I don't want to go into too many details of what went wrong over there, but what I would just like to say is that in a quantum computer, there is, a certain extra power which is there, and that has allowed to break the security of these classical number theoretic crypto systems. So let's skip some of these details. So what is the field of post-quantum cryptography? Okay, so the field of post-quantum cryptography says that we should base the hardness of our crypto systems or the security of our crypto systems on the hardness of mathematical problems for which even quantum computers have no advantage. And here the most promising is problems in high dimensional lattices. So this is what a lattice looks like. Now this is only dimension 2. What we'll be interested in is high dimension. So, something like dimension 100. And if we build cryptography from the hardness of these lattice problems, then this has the advantage that quantum computers don't know how to break those problems. And also there are extra guarantees we get, which is, a worst case to average case reduction, it is called, which basically means that breaking the crypto system implies an ability to solve hard problems in the worst case. Okay, so this is a strong guarantee. There are also other advantages, like the operations are efficient and parallelizable. And it has other interesting applications as well, some of which we will see. Okay, so if we try to do cryptography from lattices, then we can redo the old cryptography, which is we can build post-quantum versions of existing functionalities. We can also build new functionalities which are not realizable before. So we get the best of both worlds somehow. But currently, this can lead to some slowdown, so some impact on efficiency. Okay, so are there any questions so far? Okay, so the broad idea is just that using quantum computers, we can break the traditional number theoretic cryptography. So now we are trying to redo that in a way that quantum computers cannot break. Okay. And I just want to mention that, there are other options for post-quantum cryptography, like code-based cryptography or cryptography based on multivariate polynomials, hash-based, isogeny-based. So these are things which are, very actively studied in the area of post-quantum cryptography, but lattice-based cryptography is better understood amongst all of these. So as you might be knowing, the NIST, the National Institute of Standards and Technology in the United States, they ran a competition to create post-quantum cryptography standards. And they selected some algorithms among, many competing algorithms. And of these, many of them rely on lattices. Now, I just want to mention that, there was a lot of, there were a lot of setbacks during this competition, like this one post-quantum candidate, Rainbow, for example, was broken during the competition. This other candidate was also broken during the competition, right? And it is still unclear which to use. So we see that organizations are often making, or governments are often making decisions which are not very consistent with the science. Right. And the bottom line is that one cannot really ignore the mathematics of this. So one has to understand what is going on over here. Okay. So with that, I would like to come to the thing that most people are excited about, which is that these lattices, they also allow you to build very interesting new applications. Okay, so for example, suppose that you want to have personalized medicine. So then what you want to do is you want to run some experiments or, run some computation on the DNA or health records of people. Okay, so this is a quote from a magazine which captures that the dream for tomorrow's medicine is to understand the links between DNA and disease and to tailor therapies accordingly. But scientists have a problem, which is how to keep the genetic data and medical records secure while still enabling the massive cloud-based analysis which is needed to make meaningful associations. So a natural question is, can cryptography solve this? Right? Now let us look at the standard notion of cryptography. Okay, so let us look at public key encryption. How does public key encryption work? Now, most of you must be knowing that every user has a public key and a secret key. So your public key is given to everybody, as the name suggests. And then using the public key, anybody can encrypt a message for you, and only you can decrypt it using the secret key. But now it is easy to see that if I want to do this computation on genomic data or health data, then public key encryption is not sufficing. Okay, because how will I do it? I mean, secret keys in a PKE scheme, they correspond to different users. So should I encrypt, for each user? Another problem is that, if somebody has the secret key, they can read everything. If somebody doesn't have the secret key, they cannot read anything. But many of us may be willing to participate in some research or some study which reveals the output without revealing the input, right? We would like it that I'm able to contribute my data, let us say my medical data, but in a way that you cannot learn exactly my medical data. You can just use it to compute something fixed, okay, which I'm okay with. So let me give you an example. Okay, so now suppose that my secret key corresponds to some functionality and my ciphertext corresponds to some input X, which I'm thinking of as my medical data. Then what I would like is that when I decrypt these ciphertexts with these secret keys, I should be able to get only the output and not the input. So to continue the example which I was giving, if I think of F as being the age distribution of people with lung cancer. Now, this is, a sort of medical research question. And I'm using people's data to compute the answer to this question. But the people's data or the people's users' disease profile here, which is represented by X, this is actually kept hidden. So does everyone understand this concept? So the individual's input is kept hidden and just the output is recovered in the clear. Is it clear?
What related to what very like at a very shallow level related to zero knowledge?
Not at all.
Okay.
Zero knowledge is you have to prove something to someone, right? Here you are not proving anything to anyone. You're just you're trying to hide some data and you want to learn some output, like you want to compute some function. So suppose, let's take a even easier example. Now all of us have students, right? Let us say that in my class I have 30 students. I want to suppose I can encrypt everybody's data and give a key which allows to only learn the average of everybody's marks or the standard deviation and other statistical information, but does not reveal that, what were the marks that Dipro scored, what were the marks that Suprio scored, what were the marks that different students individually scored. It's only outputting what is the average. Is that more clear?
Yes, ma'am, absolutely. Thank you so much.
Yeah, so here I was using the personalized medicine example because that is a very relevant example in terms of real world application. But this example of using students, hiding their individual marks but just computing the average by giving some kind of restricted key, right? That is a more relatable example in our day-to-day lives for teachers like us, right? So here's the way that we would design such a primitive. So if I want to encrypt text, I will get some ciphertext. And when I want to generate a key for some function, I'll get a key specific to that function alone. And when I decrypt, I will learn f of x. So I will not learn x, I will learn only f of x. Okay. And security basically will say, forget the formal definition, but basically what it will say is that outside f of x, you didn't learn anything. So the functionality is telling me to learn f of x, but I should not learn anything else. Okay, so here's the example of personalized medicine which I was giving earlier. So these are, three of my friends. So we have ciphertext corresponding to all of us. And now the key is corresponding to some function. Like again, maybe it is, the average of everybody's age or the whether there is a pattern match with some disease profile or something like that. And when we decrypt, we learn only the output. We don't learn anybody's personal genomic data. Is that clear now?
Yes, ma'am.
Okay. So there is also another related concept called fully homomorphic encryption. Here what happens is that you can compute on data while it is encrypted, but you cannot give a partial key. You can only give a all or nothing key. So here what will happen is you will take some private information, you will encrypt it. Okay, and then this encrypted data is sent to the cloud or some untrusted server, let us say Google or someone. They'll compute on it while it is encrypted itself. Okay, and then the output of the computation is also encrypted, and now this has to be decrypted using the original key. So this is also an all or nothing type of functionality. Because here I don't get any partial. I cannot say that I have a key which will give me only the average of the student marks but will not give me individual marks. I can't say like that. I can only say that I have a key, either it gives me everything or it gives me nothing, but I can compute on the ciphertext while it is encrypted. I don't have to decrypt before I do the computation. Okay, is that clear? So this is some, some features of this notion. So it supports the computation, arbitrary circuit computation. It gives you a very short and compact ciphertext. And the way to think about it is that the encryption and function evaluation compute. So whether I first encrypt and then compute the function, or whether I first compute the function and then encrypt, I'll get the same output, roughly. Okay. So now let me tell you a little more about lattices. So a lattice, just a second, let me just see what other slides I have over here. Okay. So, what is a lattice? A simple lattice is basically just the integers. Okay. Can I ask what is the background of people here? Is it are you familiar with this kind of mathematics, or should I can also try to talk about more applications if that is what people are more comfortable with?
Yeah, you can talk about applications also.
So not so much this math stuff.
I guess so. Let me just see in the chat box what they say. Can you type in the chat box what do you want?
Okay, let me just briefly pause the sharing and let me just try to look at please tell me once.
Yeah, they want lattice. A couple of people want lattice, and one person wants both max and applications.
Basics required, like okay, let me continue then with the talk.
Okay.
No, so in the chat there are different things, right? So people are saying give us basics of lattices, so I'll give. Some are saying that, and then some are saying that we can do both. So we'll not have time to do both. I gave some applications, so then maybe we can just shift to lattices. I just wanted to make sure that the audience is comfortable with mathematics. Okay, so let's look at what is a lattice. A simple lattice is, so a lattice, you can think of it as a set of points with a periodic structure. Okay, this is a very high level loose English definition of a lattice. And the simplest example that we have of an n-dimensional or a high-dimensional lattice is simply the integers. Okay, so the unit vectors are going to be the basis vectors. And if I take integer linear combinations of the unit vectors, right? What are the unit vectors? 0, 0, 0, 0, 1, then 0, 0, 0, 1, 0, then 0, right? So 0, 0, 1, 0, 0, and so on. So these are the unit vectors. And if I take integer linear combinations of that, I will get these lattice points. So this is just in dimension 2. Now, you can get another lattice by applying a linear transformation to the integer lattice. Okay, so this will be that I will take sort of two basis vectors over here, b1 and b2, and I will take all integer linear combinations of that. So this is the most basic definition of a lattice. So a lattice is the set of all integer linear combinations of its basis vectors. So the basis vectors are denoted by b1 through bn. Okay. And the lattice, as I already said, is all integer linear combinations of this. So, you know, the set Bx where x is in the integers. Now, the same lattice has many different bases. Okay. So, I just want to emphasize that the basis is not unique. I could represent one lattice using many different bases. So let us define some of the, you know, core properties of a lattice. So the minimum distance in a lattice is basically the shortest distance between two lattice points. Okay, so you can see the definition here. So if I take the min over all points in the lattice which are distinct from each other, I take the distance between them, right? So the Euclidean norm of x minus y, right? Now, since the zero vector is anyway always in the lattice, because as you know, 0 b times 0 will always be 0. So whatever be my basis, if I take linear combination with 0, I'll get 0. So 0 is anyway always in the lattice. So this minimum distance can also be thought of as the shortest vector in the lattice. So the shortest vector, the length of the shortest vector in the lattice is the same as the shortest distance between two lattice points. Is that clear? Okay, so that is denoted by lambda 1, that this is the shortest distance. Now I can ask for the next shortest vector also, right? So what is lambda 2? How will I define that? So basically what I'll say is that, well, you know, let me start at the origin and I will grow a ball around the origin. When I hit the first lattice point, I will say, okay, this is the distance from the origin to this point is lambda 1. Now I'll continue to grow the ball. And when I hit the second lattice point, which is not in the span of the first lattice point, I will say that this is my second distance. So lambda 2, this is the second shortest distance. And like this, I will keep going till I get all n of the lambdas. Okay, so that is the notion of the successive minima of the lattice. And we can also define a distance function, which is to say that if I take some arbitrary point in space, then I'm going to define the mu function as the distance between that point and the closest lattice point. So it's minimum over all lattice points, t minus x. Okay, so this means that from all the lattice points, which is the closest point, first you take that. Then you say what is the distance between the given point and that point. Okay, that will be my mu function. Covering radius we can skip. We may not need it today. So now let me come to some of the problems that are considered algorithmically hard on lattices. So the most famous problem is the shortest vector problem. Okay. So here the question is that given a lattice, find a non-zero lattice vector which has the shortest length. Okay. So as the name suggests, the point is that I am given some lattice, it's represented by some basis b. And I'm saying that you tell me that in this lattice, which is the shortest vector. So how will I represent a shortest vector? I mean, any vector has to be represented using some integer linear combination of basis vectors, right? So those integer linear combinations or coefficients I'm capturing in this vector x. So the point is that I should be able to find such an x such that b times x, which is a lattice point, has length lambda 1. Okay, this is the shortest vector problem. And I could, define an approximate version of this problem as well, right? That the length of the shortest vector should be less than some lambda times, some gamma times lambda 1. So this is an approximate version of the same problem. Okay. Now another very classic problem is the closest vector problem. So here what you're given is, again, you're given a lattice represented by some basis. and you're given some target point T. This point T is not in the lattice, okay? So it is just some random point in the space. And now you want to find what is the closest vector to T, which is the closest lattice vector to T, right? This is what you would like to find. So this is the closest vector problem. And now again, you can define an approximate version of this closest vector problem. Okay, so these are the two classic problems that we have in lattices. Are there any questions about these two problems? Okay, so now let me give you a taste for how we would go about building these, building some cryptography using these hard problems on lattices, which I just showed you. So the most obvious, the simplest sort of thing that I may try to build is a one-way function. So a one-way function is defined as follows. So you have some function f which has some domain D and it has some range R. And what you would like is that this function should be easy to compute. Okay, so if I give you some point in the domain, I should be able to easily compute f of that point. So given x, I should be able to compute f of x easily. But at the same time, this should be hard to invert. So if I give you an image y from the range, it should be hard to go back to x. Okay, this is intuitively the definition of a one-way function. This is the most basic primitive that we have in cryptography. Okay, now a more advanced notion than a one-way function is something called as a trapdoor function. Now here what you have is a one-way function. So this is something that we saw in the previous slide and we have that here also. But now there is also some trapdoor for the function f. And what this trapdoor does is that if I have the trapdoor, then I can invert the function efficiently. This is the idea. Are there any questions?
No
Okay.
questions in the chat box. No. Yeah.
So we will, what I'll do is that I'll describe for another 15-20 minutes and then I'll take questions. Okay, so in the next 15-20 minutes, I'll try to give you some ideas on how we will construct one-way functions or trapdoor functions from the lattice problems that I showed you. So first of all, so I see a question. Can you read it out? Because that thing disappeared.
What mathematical concept is involved for trapdoor functions and one-way functions?
So what do you mean by what mathematical concept is involved? I mean, what I gave is a definition, right? So at that level, no concept is involved. It's just a definition of something that I want to construct. But then I will use the lattice problems in order to construct them. So that will be the concept that will be involved. Right? So I have not shown you how to construct, right? I just gave you a definition. So using the lattices, we will try to construct these, okay? So in order to give some intuition about how this will work, I thought that I will show you some pictures which will give you a sort of high level idea. So now see, we are looking at this two-dimensional lattice over here. So let's try to take a geometric view. Now I already told you that, we have multiple bases for the same lattice. Okay, so V1, V2 over here, this is one basis. Why is this a basis? You can just see by inspection, right, that if I add V1 and V2, I will get this point, right? And then if I add this point to this point, then I will get this point, right? So basically, all points will get generated if I take integer linear combinations of these two vectors. So this is a basis. Now the same thing applies if I take these two vectors also. Then also, if I take integer linear combinations, I'll get everything. So as long as the basis vectors are not linearly dependent, it will work, right? So these are two separate bases. So multiple bases we have, as we said. Now, depending on the basis vectors that we have, we can divide the space around the lattice into these parallelepipeds. Okay, so just as you can see in the picture, okay, so you have divided the space and we are getting these boxes. And if I take the second basis and divide the space, then I get these boxes. So now I'm going to, at a high level, try to differentiate between these two bases. Okay, so in the first set, the basis vectors are quite short, as you can see, and they are also quite orthogonal, right? So they are not very close together. So, you know, the parallelepiped that I get over here is almost like a square, as compared at least to this one, right? So now what happens if I have this kind of a basis? Let's take the closest vector problem. So if I take some target point T, then using the basis here, I can output the center of the parallelepiped, which in which T lives. Okay, so T lives in some parallelepiped, and I can output the center of that parallelepiped. So this will be the output. And here, just by inspecting, you can see that indeed, you know, if I stare at T, then it is natural that the shortest vector should actually closest vector should actually be the center of this box, because this T falls into this box, and this box is sort of equally spaced around these lattice points. So it seems, just by inspecting it visually, that the closest point to T should be V. Okay, but now see what happens in this case. Okay, so now here, if this is my T, then what will get declared as the closest, so just ignore this animation, but what will get declared as the closest point will be the center of this box, right? And this is the center. But you can see that these points are closer. So if the basis is of this fashion, right, like it is long and there is a lot of overlap, like the angle between them is very skewed, then we will think of that as a bad basis. And this basis will not allow me to solve this problem in a correct way. Okay. So at a very intuitive level, what happens is that, so never mind these acronyms. The point is that the problems on lattices which are hard, they are hard because you will be given some arbitrary bad basis to represent the lattice. But if I'm giving you a good basis to represent the lattice, then actually the problem becomes easy to solve. Okay, and that is the asymmetry that we exploit in building cryptography. So at a very high level, what we'll do is this short basis that we saw, this good quality basis that we saw, that will be our cryptographic trapdoor. That will allow us to, so we have to still design a one-way function, but I'm trying to give you an intuition for what will be the trapdoor. So the trapdoor is going to allow us to invert our one-way function. So is that clear?
Yes, ma'am.
Are there any questions about this? So let me go into the construction of a one-way function. Okay. So just give me a second to go into that. Yeah. Actually, before that, so since somebody was also asking for applications, let me show you an application of this lattice trapdoor. So one nice application for the lattice trapdoor is something called as a digital signature. Now, what is a digital signature? Again, it is a public key primitive. So that means that there is a public key and a private key. Everybody knows Alice's public key, but only Alice will know the corresponding private key. Okay, so in a digital signature, what happens is that you are signing messages, right? And in order to sign, you should know the private key. But in order to verify the signature, you should only know the public key. And if I can forge the signature for some user, then in that case, I should be able to prove that I'm able to solve some hard problem. So now how is this going to connect to the lattice trapdoors that we saw? So what we are going to do is we are going to take a lattice problem, okay, like the closest vector problem which I showed you. And what we will do is we will use the lattice trapdoor to find the closed lattice vector. Okay, so if I think of my message as some point in space, then I can think of the signature as the closest lattice point. Does that idea make sense? So I told you that given the good basis or the trapdoor, I'm going to use the good lattice basis as the trapdoor. So given that good basis, I'm going to be able to find the closest lattice point to the given point, right? That is what we saw. Do you want me to go back to that animation? You saw this, right? So we saw this, that if I have this good basis, then let us say T is my message. I'm going to output the signature as this point. Okay. Now anybody can verify that the distance between T and V is quite small. But without having the trapdoor, nobody can compute the point V, which is closest to the point T, because the rest of the people, the public key, will be the bad basis. So using the bad basis, you cannot compute the closest lattice point. But using the good basis, you can compute it. And this good basis will be the secret key, the Alice's secret key. This trapdoor will be that secret key, using which I will be able to find the closest point, and this will be my signature. Is it clear how we will build a digital signature? Are there any questions? So I need some feedback, because online I cannot tell how much is understood, and if things are clear, if there are questions. So please let me know. So the question is, does it mean we will use both the good basis and the bad basis? Yes, because the good basis will be the secret key. The bad basis will be the public key. Why lattice trapdoors are hard to break given quantum computers is because quantum computers can break very few things, as we know right now. So I think that, people have this idea that if I just have a quantum computer, that means I can break everything, but that is not the case. There's actually only one thing that a quantum computer does more efficiently than a classical randomized computer, so far as we know right now. And that is the computation of something called a quantum Fourier transform. So the quantum Fourier transform that allows us to, solve the periodicity problem, which is underlying the number theoretic cryptography. But underlying lattice cryptography, the problems are of a very different kind, and quantum computers are not able to break them, at least currently. Like if some new algorithm gets discovered, we cannot say, but currently it is not known how to break using quantum computers. Are there any other questions?
So there is a question in the chat box. Does
All
it mean we will use both good and bad bases for building the
I answered
algorithm?
that.
Okay.
Yeah, I answered that.
And
Yeah,
the next question, why
that
lattice
also.
backdoors considered hard to break?
Yeah, I answered that also. So would you like me to show like more? Would you like me to show something more, or should we stop here? How can security proofs for quantum key distribution be extended to realistic hardware models? So this is really open. I mean, first of all, quantum key distribution itself, there are many problems. So in quantum key distribution, you need a classical authenticated channel for the protocol to be secure. So that is already a very big problem. And then as for device imperfection, side channel and all, this is something which is still open. Right? So we don't really have a full understanding of the hardware required for these protocols. Are there any other questions? So here it says, please share some resources. So on my webpage, there are a lot of resources. You can refer to that. So I can, I can show you maybe, so one person is saying to continue with the presentation. So maybe I can show you one more cryptographic object. So this is, this is a one-way function which is built using lattices. So here, even though the connection to lattices is not very apparent immediately, it turns out that this one-way function which I'm about to show you is in fact based on the hardness of lattice problems. So here what we do is that we sample a uniform matrix A, which is fat. Okay, so it's n by m, where m is bigger than n. And we ask what we do to compute the function in the forward direction is that we take some input vector x, which is binary, and we compute the matrix vector product of A and X. So we compute A times X. And I'm claiming that this is a one-way function. So I would like you to sort of challenge this. Why can I claim this is a one-way function? Who thinks that, so if I'm giving you A and I'm also giving you A times X, then can I not recover X using Gaussian elimination? What do you think? So I would like you to tell me how can I claim this function is one way? So in this function, what I have given you is I've given you a matrix A. I've given you some input vector X, and the output is A times X modulo Q. Okay, so Q is some large prime. And my question is, why cannot I recover X using Gaussian elimination? Just do matrix inversion, right? I'm given A. So why can't I compute A inverse AX and get X? Who can tell me? So here I've stated a theorem that this function AX mod Q is a one-way function, which means that I'm claiming that given A and AX, nobody can recover X. And my question to you is, why can't I just do Gaussian elimination and recover X? That is my question. So who can tell me? I would like somebody to try. Is the question clear?
Can you repeat the question, please?
The question is that if I give you A and AX, then why can't I compute X from that?
There's an answer in chat box saying it is because it is normalized one.
No, I don't know what you mean by normalized. I'm just giving you a matrix A and I'm giving you A times X. This is all happening over a finite field, ZQ. So why cannot I just invert the matrix and recover X? That is my question.
Like, it's because it's not square, or we need to do some kind of a pseudo inverse or something.
Make it square. I mean, so right now there are fewer constraints than equations, right? So you could always add a few random constraints and make it a square matrix and then invert it. What do you mean by non-linearity? It's a linear system. So the answer is because I'm imposing a constraint on X being binary. I'm saying that I need X to be binary. So even though I can do the inversion, I will, in general, when I do the inversion, I will get some large entries in the vector X. Okay, so I will not get a binary X. So that is why simple Gaussian elimination does not work. So this is a one-way function which is based on a lattice problem. Now why is this a lattice problem? That is a little more technical and maybe that is outside the scope of today's talk. So I will stop here. And if there are any additional questions, I'll be happy to take those.
Ma'am, does that mean like the constraint which you imposed in the example, we can impose other similar constraints for different applications or different functions?
No, it does not mean that, because it needs a rigorous proof that by imposing this constraint, this becomes a hard lattice problem. So we cannot just impose a constraint and hope that this makes it hard to solve. We have to have some rigorous justification. And in this case, there is a justification, but that is showing that proof would be outside the scope of a talk, like it would need a few lectures. But
Okay.
but what I was trying to say was that this function appears very simple, and why is it that it is why is it not trivial to solve? This is what I wanted to point out, that it's because we are asking for short vectors. So intuitively you can think of it like that, right? That this I want a short vector in some lattice. It will actually exactly correspond to that. So if I look at if I look at the lattice which consists of all the vectors orthogonal to A, okay, and I am asking you to find a short X such that A times X is equal to 0, then isn't this exactly equal, like this is equivalent to the problem which I had given you earlier, right? Which is to find a short lattice vector. So that is why that particular function is one way, believed to be one way.
Okay, ma'am. Thank you so much.
Yeah. Any other questions? Okay, then if there are no other questions, we'll stop here.
Yeah, sure. Thanks a lot, Professor, for your time and for the excellent talk.
Yeah,
Thank you once
all
again.
right. Thank you.